Okay, so what we're going to do in the rest of this lesson is talk about what's called the net change theorem, right? And what we're going to basically talk about is what the definite integral represents beyond just a net signed area. Okay, so the fundamental theorem of calculus part 2, we can kind of rewrite it. And I see that I've got a wrong word here. So this should be and. Okay, so the integral of a rate of change, the integral of a derivative, right, equals the net change over that interval. So if we have the definite integral of a rate of change, okay, a rate of change, so of a derivative, a rate of change, we know that that's equal to, remember, we take the antiderivative here, so it would just be f. Okay. Notice that this would be the beginning of the interval, or sorry, the end of the interval, where that function was at the end of the interval, f of b, and here f of a is where that function was at the beginning of the interval, which makes a net change. Okay? So if you integrate a derivative, a rate of change, what you're going to get is the net change of that function over the interval. So that equals the net change of f over the interval a to b. Okay, and this is called the net change theorem. So a couple of, just without doing it with too many numbers, but just kind of looking at a couple of examples on kind of a top level. And the worksheet for this lesson goes through some with more details, more actual numbers in them. So let's say you had the volume, a volume function. It tells you how much water is in a reservoir at a specific time. So its derivative is going to be the rate at which water flows into, or I guess it could be out of, the rate of change of the volume. And so if we'll assume in this case water is flowing in, okay? So it's the rate at which the water is flowing in. And that's something that you would know if you were working, at a dam or something like that, and you were letting water into the reservoir, you would know the flow rate, right? And so if you were to integrate from time 1 to time 2, that flow rate, what it's actually equal to, right, is the change in, I should have said time 2 there instead of B and A, right? Time 2 and time 1. So it's the change in the volume over that time interval. So it has a meaning beyond an area. Okay? Same thing with number 2. If we have some population at time t, and we know how that population is changing, which is another thing that happens a lot in biology, wildlife science, is we can tell how a population is changing, but we don't necessarily have an equation for its population. But we do know, we can say something about its rate of change. Okay, so again, if you were to integrate over a period of time that n prime of t, then you're going to get the change in the population, okay, over that interval. All right, I'm going to skip 3 for a second because I want to focus a little bit more on the motion interpretation of this that we have been doing, these kind of motion problems for a while. If you have a position function, okay, then what is the rate of change of the position function? It's the velocity function, right? So if you were to integrate over a specific period of time the velocity function, you're going to get the change in position. over that interval. Okay. And of course, if you were to integrate the acceleration, you're going to get the change in velocity over that same time interval. Okay, but we got to be careful, because is the change in position equal to the total distance traveled? And when we first talked about this, don't remember which lesson it was, we showed some diagrams about how those are not always the same, right? So let's say we have an object that moves one direction, and then, you know how we've done our motion diagrams, it's moved another direction. So this might be S of T1. This might be S of T2, and this might be S of T3. Okay. If we were to integrate from T1 to T3, that velocity, we are only going to get this distance right here. Right? That is the change in position. That is S of T3 minus S of T1. Remember, we called that displacement way back in the original lesson about this. Okay. That does not give us the total distance traveled. So in order to find the total distance traveled, we have to find these points in between the T1 and the T3 where the object stops and changes direction. Okay. And how do we know when an object is stopped? It's when its velocity is 0, right? So then we can compute this distance and then this distance, but we have to have this middle t value and then find its position as well, right? So if we look at it, I'm going to kind of break it down. S of, sorry about that, S of T1 over here to S of T2. Now, if we do S of T2 minus S of T1, you're going to end up with a negative number because it's moving to the left. It's moving in the negative direction. And when we're doing distance traveled, we don't want that. So we're going to need to put absolute values around it. Okay. And in this case, you could think of that as, again, the integral of the absolute value of velocity, because we don't want things to be signed positive or negative, right? From T1 to T2. And then to get that second part from T2 to T3, in this case, because it's moving in the right direction, we could do it without absolute values, but if we want to guarantee that everything is positive, then it helps to just use them. So in other words, when you are trying to find total distance traveled, we need to add absolute values to the velocity function so that we're counting everything as positive. Okay. So let me give you an example. It is possible for you to go ahead and find that T2, plug it in, and just calculate each distance without doing an integral. Okay. But I'm just going to show you an example. Okay, so we have a velocity function. Whoopsies. Sorry about that. We have a velocity function. So we're going to have to find an antiderivative to get the position function in either case. So we are trying to find the displacement and the distance traveled. So the displacement is the easy one, because all we have to do is integrate the velocity function over the given interval. No absolute value is required. But in order to do the distance traveled, we need to add absolute values, which means we're going to have to break it into a piecewise function. We have to figure out where is it 0, when is it positive, when is it negative, etc. Okay, so let's go ahead and finish the displacement first. From 0 to 3, so that gives me 27 over 3 minus 9 minus 0, which turns out to be 0. So it looks like this object started and ended in the same place on that interval, 0 to 3. So there was no displacement, but I'm quite sure that there was some distance traveled. So let's set this t squared minus 2t equal to 0. We figure out which t values it is actually equal to 0. And then we're looking at a sign chart. I mean, it's 0 at 0, but I'm not going to be talking about a time less than 0 anyways. So I'll plug in like a 1 to this, I will get a negative, and I'll plug in like a 5, and I will get a positive. So that means I'm going to need to integrate from 0 to 2 and from 2 to 3, because from 0 to 2, it's moving to the left, and from 2 on, it's moving to the right. Now, when we do the absolute value, what do you do to the function on the interval where it's negative? Do you keep the function the same? No, remember, you take its opposite. So this will be 2t minus t squared, which is just this times a negative. Okay. And on the interval where the function is positive, the absolute value is just equal to itself. So there we will integrate just the t squared minus 2t. And then we've already kind of done the integration above. And now I'm going to be plugging in different numbers. So let's see, when we plug in 2, we'll have 4 minus 8/3. We plug in 0, that's just 0. When we plug in 3 to this, we know we get 0 minus, and then I'm going to plug in 2 8/3. I better put parentheses around that. 8/3 minus 4. So that would be 8 plus 16/3, which is 24 40/3. And so what that did is this integral counted the part of the movement that went to the left. So this particle object, I'll draw it up here, is going like this, and then it turns around and goes like this. This is at t equals 0, this is at t equals 2, and this is at t equals 3. And so we're counting this left-hand distance here and this right-hand distance here. Graphical interpretation of this, just because we've talked about this already before. The object moves t squared minus 2t. So here is a graph of the velocity. And we were looking at the interval from 0 to 3. So from 0 to 3. So when we integrate that, that kind of gives us these two regions. I'll call this A1 and I'll call this A2. Okay. So when you calculate displacement, you're doing net signed area. So it's going to be the area above minus the area below. But when you're doing distance traveled, everything is considered positive. So instead, you're going to have A2 plus A1.